So I'm going to take you through the last couple examples that we did not do last class. You may want to pause the video as we go and try them on your own. So remember, the steps are that we're going to do our y-intercept. Find the y-intercept. You're going to plug in 0 for x in the original equation. So I'm going to get 19 over negative 76. What does that reduce to as a fraction? It reduces to 1/4. So my intercept is at 0, negative 1/4. So I'm going to plot my y-intercept. And now I have to find my x-intercept. The x-intercept, remember, we set our y value equal to 0 over here, but our first step is to multiply the denominator to the other side of the equation. Anything times 0 is 0. So now I have 0 equals 19. So the shortcut is to set your numerator equal to 0. Will 19 ever equal 0? No. So there is no x, or I'm just going to write none. So there's no x-intercept. Now we're going to do our asymptotes. To do our vertical asymptote, we're going to set the denominator equal to 0. So I would add 76 to the other side and then divide by 38. So x would have to be 2. If x is 2, the denominator is undefined. So our asymptote is at x equals 2 because we cannot let x ever be 2, or our function will be undefined. And then our last step is our horizontal or slant asymptotes. Where is the power for x the biggest? It's biggest in the denominator, a linear function down here, a constant function up at the top. So degree of 0, degree of 1. Denominator wins. It will have a horizontal asymptote at y equals 0, which is why we had no x-intercept. So I can see what this elbow of my graph is doing. And I'm not sure where the other elbow of the graph is going to go. Does it go up here or does it go down here? So I'm going to plug in the value either 3 or 4 or 5 in the original function to see what I get. So if I plug in a value of 3, 19 divided by parentheses 38 times 3 minus 76 is 1/2. So at 3, my graph is at 1/2, which is right here. So there we go. Now I can answer my other two questions. The domain of the function is going to be similar to our vertical asymptote, but this time x cannot equal 2. Our range of our function is equal to the horizontal asymptote, so y cannot equal 0. And the limit analysis, this is telling you to look at the right side of the graph. What's happening over here as x goes to positive infinity? The y values are approaching 0. So f of x is approaching 0. And what's happening over here is the x values are going to negative infinity, and so the y values are going to 0. And as x approaches 2, this plus sign means look at the right side. So here's my asymptote. Here's the right side of the asymptote. See how it's pointing towards positive infinity? So positive infinity right there. And the left side of that value over here, it's going towards negative infinity. So negative infinity. So that was example 2. All right, so we're going to do examples 3, 4, 7, 8, and 9. And my recommendation again is to kind of pause the video as you go and try it on your own first. So example 3, I plug in to get my y-intercept, I plug in 0 for these x values. So I get negative 1/6. So 0, negative 1/6. For my x-intercept, I look at the numerator. The numerator can never be 0. So I have none again. My denominator is bigger again. So, oops, that's going to be y equals 0. Oops. I didn't do my vertical asymptotes. My vertical asymptotes are where the denominator is 0. I need to factor my denominator. So what are the factors of negative 6 that would add up to negative 1? That would be negative 3 and positive 2. So my vertical asymptotes are at positive 3 and at negative 2. So x equals positive 3, x equals negative 2. So I have two vertical asymptotes at 3 and at negative 2. This is a little bit trickier graph. There are three different regions of the graph. So I'm going to show you how to do these two regions out here, but this section is a little bit trickier because it crosses the x-axis. So I think you would look at a calculator for this section of the graph. Let's plug in 4 and see what we get. So if I plug in the number 4, I get 1 divided by, I would get 1 here, and I would get 6. 1 over 1 times 6, 1/6. I can't do this in my head. It's the end of the day. I'm getting 1 divided by 4 squared minus 4 minus 6. Is that 1/6? Okay, so I was right. So at 4, I'm at positive 1/6. So this elbow is up here in positive land. What about when I plug in negative 3? When I plug in negative 3, I get a negative number here. So I get negative 6, and I get a negative number here, negative 1. So I'm also at positive 1/6 on this side. So the only funny thing is what's going on in this middle section. So let me show you. This is a tricky one. X squared minus x minus 6. So this is probably not a graph I would have you do by hand. Maybe I would ask you like part of this, like what's the vertical asymptotes or something, but I wouldn't expect you to be able to get that this section is the upside down parabola, just because sometimes these graphs are tricky and they poke through the horizontal asymptote. So I myself would have double checked this one with a calculator. So we can say that our domain x cannot equal 3 or negative 2, and our range y cannot equal 0. The only reason I saved domain and range till the end is because I'm going to show you something interesting that happens on example 4. Usually the domain and range are just going to relate to the asymptotes. On number 4, there's a little bit of an exception to that. So on example 4, maybe pause the video, try at least answering this part on your own, and then maybe unpause it to check out the graph. So pause it now. So I'm going to do my y-intercept. I'm going to plug in 0. So I would get 7 over, let's see, this is negative 5 squared, positive 25. So 7 over 25 is kind of a really small number right there. My x-intercept, again, none, because I have 7 in the numerator. My asymptotes, x cannot be, or sorry, I'm going to write x equals 5 because it's my asymptote. So x equals 5. 1, 2, 3, 4, 5. And my horizontal asymptote is at 0 because the denominator is bigger again. So this elbow of the graph looks like it's going up. So what's this side doing? So something interesting happens because the denominator can never be negative, right? Anything squared is always positive. When I plug in 6, I get 7 divided by 1, which is 7. So this, what did I say I plugged in? 6, comma 7 divided by 1, which is 7. So here's my volcano-looking graph, which does affect the domain and, well, it affects the range. My domain is still x cannot be 5, but what's my range? I actually have no values down here. So unlike this range, just y does not equal 0, this range is all positive y values. Y is greater than 0. So I usually just wait and do domain and range at the end so that I can see what the graph looks like before I answer that question. For those of you who weren't here, we already did 5 and 6 together yesterday. So we've got 7, 8, and 9. So again, pause the video, try them yourself, and then come back and check. So for our y-intercept, I'm plugging in 0 here, and I'm just going to get 1. So 0, comma 1 is my y-intercept. My x-intercept, set the numerator equal to 0. So 2x equals negative 1, and x will be negative 1/2. So negative 1/2, comma 0 is my x-intercept. My asymptotes, where is the denominator 0 when x equals negative 1? And my horizontal asymptote, the powers are equal, x over x. They're both linear functions. So I'm going to strip the coefficients, and 2 divided by 1 is 2. So this actually has a horizontal asymptote at 2. And you can kind of see how this is going to bend. There's my elbow bending. And then I'm probably up here in this quadrant because I have no other x-intercepts. But good practice, I'm going to plug in negative 2 and see what I get. So I would get negative 3 in the numerator and negative 1 in the denominator. So negative 2 comma 3 is my other elbow. So I have graphing on top and bottom. So this time my domain is just x cannot be negative 1 and y cannot be 2 like I'm used to getting. What's happening as x goes to the right? We are approaching our asymptote, right? So our asymptote was at 2, so the function's approaching 2, and same thing in this direction, approaching 2. What about at our vertical asymptote at negative 1 from the right side? Negative 1 from the right side is pointing downwards, so negative infinity, and negative 1 from the left side is pointing upwards towards positive infinity. Okay, last one. Oh no, number 9 too. So we plug in 0 to find our y-intercept. So we would get 0, comma 1/4. There it is. To get our x-intercept, we set our numerator equal to 0. So there is none. Our domain, we look at our denominator, x minus 2 times x minus 2. So x cannot be, or I'm going to write x equals 2 because it's an asymptote equation. So x equals 2 is our vertical asymptote. The denominator is bigger as a power, so y equals 0 is our horizontal asymptote. So I can see that this elbow is going through that point. Probably we're down here, although this is x minus 2 squared. So I think this is going to be the volcano-shaped graph. The denominator will never be negative. So maybe plug in positive 3. 1 over, if I plug in 3, don't I get 1 times 1 is 1, so 3 comma 1. So it is a volcano graph. Everything is positive this time. And my domain, x cannot be 2. My range, y is strictly greater than 0 this time, because all of my function is up here. Let's do our last analysis. As x goes to the right, the function approaches 0. As x goes to the left, the function approaches 0. As x gets closer to 2 from the right side, the function approaches positive infinity. As x approaches 2 from the left side, the function approaches positive infinity. So last but not least, we can do this the same way, right? So my y-intercept, plug in 0, I would get 0 divided by 1 is 0. The x-intercept, where is the numerator 0 when x is 0? So it should make sense that they have to be the same, right? If there's a y-intercept that's 0, 0, there's an x-intercept that's 0, 0. My vertical asymptote is at 1. And I am going to have a slant asymptote because I've got x cubed divided by a quadratic function. So I need to do the box method. To do the box method, you need to be able to see your divisor. X minus 1 times x minus 1. If I FOIL this out, is x squared minus 2x plus 1. So I'm going to take x squared minus 2x plus 1 and do division. So you put your whole divisor down the right-hand side of your box, or left-hand side of your box. You're going to put x cubed inside this box. That's your dividend. You have 0 of anything else. So you have to put x up here. X times negative 2x is negative 2x squared. X times 1 is x. What needs to go here to make this 0? 2x squared. That way that adds up to 0. So this is just going to be a 2. 2 times x squared is 2x squared. This is your asymptote right there. Everything else is going to be remainder, so I'll show you the remainder, but you don't have to do the remainder. So I'd have negative 4x plus 2. So this has to add up to 0, so this would be positive 3x as my remainder. This has to add up to 0, so my remainder is 3x minus 2, which I don't really care about. I have a slant asymptote at y equals x plus 2. I'm not going to have you do the analysis because I didn't write it down. You go to 2 on the y-axis and put your dotted in asymptote. So this asymptote, or this function, must come up, touch that intercept, and scoot back down, I think, unless it does some funky turn. This would probably be a good one to check on my calculator because cubic rational functions might have something funky going on. So we might want to check on our calculator. Comes up. Ooh, look at that trick. So instead of it coming down, it actually flipped and then followed this up vertically. So I would not expect you to know that without looking at a graphing calculator. Then this part of the function behaved as we thought it would up here. So, I mean, if you had a really complicated problem, maybe I would just ask you like, hey, what's the x-intercept of this? Or what's the slant asymptote? Putting it all together would be kind of unfair without looking at the graph based on how funky that little flip was. Let's see, the domain would be x cannot equal 1, and our range is all real numbers, right? Because it goes forever. So I hope that helped you review some rational functions, and I think sorry, I was trying to grab the correct paper. So because this video is already 17 minutes long, I'm going to have you complete as your guided practice for today only the front page of 21. So they're kind of like one-off questions. Find the vertical asymptotes of this. Find the intercepts of this. So only do questions 1 through 12 as your assignment, and you can just upload just the front page into Google Classroom. And then we'll start when we get back after vacation with these pages. So you only need to complete numbers 1 through 12 and upload that as your practice for today into Google Classroom. Thanks.